Good afternoon, everyone. Welcome to Week 12 interactive session. We will wait for a couple of minutes and then get started by 5. Let's get started. Let's start by looking into the concept of working set model. Basically, working set model gives us the estimate of the locality of the particular process actually. So it gives an estimate on the locality of reference. So for demand paging, as the number of page calls decreases, the performance of the system also improves. So working set model tells us what is the locality of a particular process. It means that at a given point of time, the program or process always have this tendency to refer to something that it have already been referring or refer to something in the same locality, right? So if we are able to track this, like at a given point of time, if the process is using this set of pages, and at a later point of time it is using a similar set of pages, so this gives us an estimate of the a number of active pages at any given point of time. And then if you are able to ensure that this working set number of pages are there in the memory, we can bring down the number of page faults. So that is this concept of working set model. So how it is seen that, for example, at a given point of time, T1, T2, T3, TN, we see the last n window size of the working set. So, for example, page 1, page 2, page S, and at T1, T2, we see what are the last n pages are referred. Same way, some PX, PY. Similarly, we check how the working set, this is the working set at T1, this is the working set at T2. If the particular program's locality is very high, it might be keeping on, even though, for example, if we give the working set window as 5, but the current process is executing the codes which is distributed across P1 and P2, it can happen that the working set will have only P1 and P2. Though it doesn't mean that the program doesn't use any other pages, but it means that in the last 5 references, all have been to P1 and P2. Again, it can be that at T4 also, it can still be P1, P2, and maybe one more, it referred one more, that is P3. So as the process execution moves, this working set also varies. But if you are able to get an average of the number of frames in the working set, then we can ensure that these many pages are there in the memory, and then bring down the page fault number. So let's quickly take an example just to understand what this concept is. Yeah, let's take a working set window as 5, and the page reference string for the particular process is 2, 6, 1, 5, 7, 7, 7, 5, 1, 6, 2, 3, 4, 1, 2, 3, 4, 4, and 4. So if this is the reference string for the particular process, and the working set window is given as 5, let's see how actually hello, am I audible? Hello. All right, I think yeah. So at T1, the process is this is the first reference, okay? And this is the working set that we will be having. So when page 2 is referred first time, the working set will comprise this particular page. We are seeing the last 5 reference as the working set window. So at T2, page number 6 is referenced. So the last 5 references will include 2 and 6. Now at time T3, when the next page is accessed, the working set grows. Now at T4, when the next page 5 is accessed, 2, 6, 1, and 5. forms the working set of this process. Now at T5, when page 7 is accessed, again the working set for the last, since the working set window is 5, we take the last 5 references, which is 2, 6, 1, 5, and 7. Now at T5, to T6, again the page 7 is only referred. Page 7 is referred. So now if we take the last 5 references, the working set will be 7, 7, 5, 1, 6. So working set will comprise the last 5 references. So 6, 1, 5, and 7. So you can see here that since the locality came into picture, the process have been accessing the page 7. We can see that the working set is actually now contains only 4 frames. Now at T7, again frame 7 is only accessed. So if we take the last 5 references, it is 7, 7, 7, 5, and 1. So working set will comprise 1, 5, 7. Now again 5 is being accessed. T8, page 5 is accessed. So now if we take the working set, it will be 5, 1, 1, 2, 3, 4, 5. So in the last 5 reference, only 2 pages have been accessed, which is 5 and 7. Now let's, the next access is page number 1. T9, page 1 is accessed. So now let's see the working set. It is 1, 5, and 7. The last 5 access comprise 1, 5, 7, 7, 7. 1, 2, 3, 4, 5. Right. Now at, maybe we can come this side. T10. After 1, the 6 is accessed. So when 6 is accessed, the working set grows again. 1, 5, it will be 6, 1, 5, 7, and 7. So at T11, the page that is accessed is 2. So now the working set window becomes 2, 6, that is 1, 2, 3, 4, and 5. So 2, 6, 1, 5, 7. 1, 5, and 7. Now at T11, T12, we are referring 3. When 3 is referred, let's see the last 5 axes include 3, 2, 6, 1, and 5. So as we can see that this keeps shrinking and expanding. At T13, when 4 is accessed, working set becomes 4, 3, 2, 6, 1. At T15, T14, when 1 is accessed, working set become 1, 4, 3, 2, and 6. At T15, when 2 is accessed, again working set becomes 2, 1, 4, 3, 2 again. So it is 1, 2, 3, 4, 5. So the last 5 axes includes 2, 1, 4, and 3. At T16, when we access page number 3 again, the working set becomes 3, 2, 1, 4, and 3. So now 17, when we access page number 4, working set become 4, 3, 2, 1, and 4. At T18, we again access 4. So working set becomes 4, 3, 2, and 1. At T90, again we access 4. So it becomes 4, 3, and 2. Now, for this particular process, if we need to bring down the page fault, so the average number of frames required will be equal to, we call it sigma working set of divided by the total number of references. So if you see here, what is the size of working set here? So this is 1, 2, 3, 4, 5, 5, sorry, 4, 3, 2, 3, 3, 4, 4, 4, 4, 5, 5, and 5, 5, 4. So when we sum it up, it becomes 1 plus 2 plus 3 plus 4 plus 5 plus 4 plus 3 plus 2 plus 3 plus 4 plus 5 plus 5 plus 5, 3 plus 4 plus 4 plus 4 plus 4 plus 3. So it is coming around 71 divided by total number of references is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. So we have 19 references by, so which gives it around 3.73. So if we have around 4 frames for this particular process, we can ensure that majority of the times the working set will be there in the memory, and thus will bring down the page faults. Okay, so this was about working set. The other concept that was discussed in the class was about the other factors concerning demand paging. So they are majorly pre-paging, the page size, the TLB size, the program structure, etc. So if as it's already discussed, that pre-paging is to ensure that the initial, for example, when a process first time comes in into the memory for the first time, since none of its pages will be available, so there will be a huge page fault in the initial phase, followed by, once the working set comes into the memory, the page faults will be kind of constant. Then as the process move to a different locality, its page fault will again increase. So we will have something like this. It will be, so we will have highs and lows. So this is the if this is page fault, and so this will be the initially, since working set is not in memory, page faults increases, then it decrease, and this is when the working set is in the memory. Again now, when the program move to a different set of locality, some function invocation or anything, and then again it need to bring in the working set in the memory. Then once the working set is in memory, the page fault drops and it becomes a kind of constant for some time. So one can remove this particular initial page fault storm or spike by doing what is called as pre-paging, where we bring in already we bring in some pages of the process. So it works best when we already know the know about the process, and we know which would be the initially accessed process and all. Then the another aspect that actually affects the paging is basically the the structure of the program. Like, for example, in a program, we have, let's take the example of a program where we have a for loop. And we have a 2D array. If A of I j is accessed. One this and what if it is the other way around. So this is one way we normally would be accessing, that is on a row basis. So if we have the memory in the row major order, and if we are accessing it in that manner itself, then this would increase the locality and brings down the page fault. Whereas if we have a row major order storage, and if we access it in column major order, then we will have for every axis we will have a page fault. For example, if this is a size of 128 into 128, and if we are assuming that our page can hold one row that is 128 elements. Then in the first scenario, we are starting with I equal to 0, and then we are accessing all the 128 elements here. Then this is I equal to 0. And then we go to the in the next iteration. So after this inner for loop iteration, after I gets incremented, we go here, and then the 128 entries gets added. So the number of page walls here would be only 128, which is the number of this outer loop. Whereas in the second scenario, we still have I equal to 0 and all the 128 entries added here. But how are we accessing? First, we access A of 0, comma 0. Then we are accessing A of 1, comma 0. Then we are accessing A of 2, comma 0. So every iteration of this inner for loop, we are going to the this is first iteration. We are going to the next, and then we go to the next page. So here the page fault number actually increases. So for every inner iteration, we will be going all the way till 128. Then we have to come back to again 0. So the number of, for every axis, we have actually a page fault here. So this also, so the structure of the program also it sometimes depends, like affects the number of page falls, and thus the performance. So now let's look at the other concept that was discussed in the previous class, that is on secondary storage and disk scheduling, yeah, file system and secondary storage, then storage hierarchy, disk structure, disk scheduling. Um, Storage. So in secondary storage, basically is where we store majority of the data, and whenever it is needed, we bring those data to primary memory or the RAM, and then we do the execution. So typically, one such secondary storage that we are considering here is hard disk drive. Okay. So typically, a hard disk drive is have a cylindrical kind of a structure, wherein we have something called as, we call this as a plate, and on every plate we have some circular rings called track, all these circle is a track, and on each track, there is something called a sector. So if this is these forms the sector. On each track, there is something called a sector, and data is stored in this particular sector. Data is normally stored in the sector. Okay, so these are the sector where data are stored, and in general we read and write in terms of sectors. Okay, so this is when we have a single plate. If we have multiple plates, it's like multiple plates arranged in line. There will be a arm using which the read write will happen. So all of them can read from the same number or same track at a given point of time. And if you visualize, this looks like a some tracks gives a cylindrical shape, right? So it is alternatively another term that is used for track is also a cylinder number. Okay, now let's so if someone want to if I want to access any memory from the secondary storage, this access time is much higher than the primary memory access time. So basically, when we need to access it from a particular sector, which is on a particular cylinder or a track, first this memory head has to come and position itself on that particular track or cylinder. Okay, so this arm will either move in the front or in the back direction only. So it first need to come to the particular cylinder, and we call it as the seek time. Okay, and that time is called the seek time. So it's a time to move the disk arm to the desired cylinder. Okay, so it is called the seek time. And then, for example, we have the data currently present here, but the arm is here. So now this plate has to rotate. It has to rotate, and this has to rotate, and it should come here, so that we can do the reading. So this time it takes to rotate and come here near the head is called as rotational latency. And once the rotational it reaches here, we have some. Then we will start initiating the data transfer. So transfer latency. So any memory access thus comprise of so average access time in case of secondary storages thus average seek time plus average rotational latency plus average transfer time, data transfer. Plus any other overhead if it is mentioned, any controller, disk controller related overhead if it is mentioned that. So this counts to the overall time it requires to read any data from the secondary storage. Okay, now let's before getting into the disk scheduling and other thing, let's take some examples. So, and understand this latency concept first. So, let's take one question. So, yeah, it's given that the total storage capacity of a disk, total storage capacity per disk having 80 tracks storing 128 bytes per sector is 163840 bytes. How many sectors does the disk have? Okay, so as we have seen here, the disk can have n number of sectors. This is sorry, n number of track. This is one. This is two. So this is three, and we can have n such tracks. This is n. Okay, these are the tracks. And on each track, we have what is called as this sector. Okay, so let's assume that, and each sector will hold a certain number of bytes. So let's assume that there are n sectors. Assume that we have x sectors. Okay, it is given that, and we know that all the sectors per track. Okay. So how many tracks are there? We have 80 tracks. So on 80 tracks, so if we take X sectors per track, we will have 80. Oh, sorry, X doesn't suit here. S sectors, so 80 into S. Okay. Will be the total number of sectors on the whole disk, and it is given that each of the sector will store 128 bytes into 128. So this will be the total storage on the disk. Okay, so take this example. So if this is if in the, we have 80 such tracks, and we don't know this number. This number is what is, this number is what is not known. Okay, so on any disk, the number of the total bytes stored will be the number of sector into number of tracks into the capacity of each sector. Okay, so bytes total capacity will be number of tracks into sectors per track into bytes per sector. Okay, so here it is given that the total capacity is 163840. 163840. 163840 is the total capacity, and number of tracks is given as 80, and we don't know the number of sectors, so we keep it as a variable, and the number of bytes per sector is 128. So S will be equal to 163840 divided by 80 into 128, which is equal to 163840 divided by 28 into 80, which is 10,240 divided by 10,240 equal to, which is 60. So the total number of sectors here is 16. Okay. So that was one question. Now let's take another question wherein we'll try to compute the access time and all that. Okay. So given a disk with following a disk with 16 surfaces, 16 surface implies that this is 1, this is 2, this is 3, this is 4, like that. 16 are there. Okay. And on each of the surface, we will have tracks and sectors. So 128 tracks per surface, 256 sector per track, and 512 bytes per sector. So these are given. Okay, now let's compute what is the disk capacity. So as I just mentioned, this capacity will be the number of tracks into sector per track into byte. This is for one particular surface. So if we have n different surface, it will be n into, where n is the number of surfaces. So here we have, so capacity will be 16 surface into 128 tracks per surface into 256 sector into 512 bytes, which is 2 power 4 into 2 power 7 into 2 power 8 into 2 power 9, 2 power 8, 2 power 28, which is equal to 256 MB. So the total capacity is 256 MB. Another question from this is, if number of bits required to address a sector. So we have to find the total number of sector and then decide how many bits are needed to address the sector. So total number of sectors is 2 power 4 into 2 power 7, number of surface into number of tracks per surface into number of sector per track, which is equal to 2 power 19, which implies that we need 19 bits to address sector. Sector. Okay. This is another part is, if it is given that the disk is rotating at disk is rotating at disk is rotating at 3600 RPM, which means 3600 rotations per minute. What is the data rate, data transfer rate? So we know that when the disk is rotating, it goes over the full sector, and how many bytes are there on that particular track, those many bytes will get transferred. Okay, so in one, let us see what is the number of bytes in a particular track. So in a particular track, we have 256 on a track. We have 256 sectors, and each sector have 512 byte. Okay, so which is nothing but 2 power 8 into 2 power 9, which is 2 power 17 bytes. So this in one rotation, this whole 2 power 17 bytes can be transferred. Okay, so in one rotation, because this is how the sector is, right? So this is how the sector is. So one rotation will takes, okay. So in a sector, this is how on a track the sector is. Like this way it will be. And when one rotation is done, the whole data that is stored in this track will be red. So one rotation will cover this whole area, this whole sector, and the whole number of data that is stored there will be transferred. One rotation, 2 power 17 bytes will be transferred. Okay. Transfer rate is nothing but transfer rate equal to bytes per second. So now we need to find how many rotations are there in 1 second. Okay. It is given that we have 3000 rotations in 1 minute or 60 seconds, which implies that in 1 second, so in 1 second, we will have 3600 by 60 rotations, which is 60 rotations. So in 1 second, we have 60 rotation, and one rotation can read how many bytes? 2 power 17 bytes. Okay, so this is with respect to one surface. So we have, so for one surface, we have in 1 second, we can transfer to power 17 into 60. Now for the whole disk, we have 16 surfaces, which makes it 2 power 4 into 2 power 17. 2 power 4 is 16, okay? 60, which is 2 into 2 power 20 into 60 bytes, which is nothing but 120 bytes per second. So the transfer rate across the disk is 120 megabytes per second. Okay, now one more follow up on this is if the rotation speed is if rotation speed is given as 3000 rpm, what is the average access time? With a seek time of 11.5 millisecond. Okay, so access time is nothing but average access time is the time it takes for the head to come to the particular cylinder, which is nothing but seek time. Then the sector has to come to the head, which is nothing but rotational latency, rotation time, plus any other overhead if it is mentioned. So as of now, no overhead is mentioned. We'll take it as 0. Okay. It is given that seek time is 11.5. Seek time is given as 11.5 millisecond. What we need to find is the rotation time. Okay. So it is given that there are 3000 rotations in 1 minute. So in 1 second, we have 3000 by 60, 50 rotations. So we can see it as 50 rotations take 1 second, or 50 rotation take 1 second. So one rotation will take 1 by 50 second, which is equal to 0.02 second. 0.02 second. Okay. The rotational latency is normally taken as half the time. Okay, half of the time it takes for a complete rotation. So average rotational latency is normally taken as the time to rotate half the disk. So rotation latency becomes 0.02 by 2, which is 0.01 second, which is equal to 10 millisecond. Okay, so now the average access time will be it is given as seek time, which is 11.5 plus 10, which is 21.5 millisecond. That is the average access time. Now let's see one more question and then go about to disk scheduling algorithms. So the next question is, what is the average access time for transferring 512 bytes with the following disk specification? Following disk spec. So average seek time is given as 5 millisecond. Rotations are given as 6,000 rotations per minute. Then data rate is 40 kilobyte per second, and controller overhead is given as 0.1 millisecond. So as we know, access time equal to seek time plus rotation time, not rotation, actually, average rotation latency. Rotation latency plus transfer time, data transfer time, plus overhead. So we are given with overhead, we are given with seek time. So we need to compute the rotation latency and the average data transfer time. So let's see the rotation latency. So it's given that 600 rotations per minute. So in 1 second, okay, let's compute the rotation latency average. So in 1 second, we will have 600 by 60 rotations, which is nothing but 100. So time for one rotation, 1 by 100. Zero 0.01 second or 10 millisecond. Now, average rotation latency is average rotation time equal to half of this, which is 10 by 2, which is 5 millisecond, is the time it takes for half a rotation. Okay, so it is 5 milliseconds. So we are done with the this component. So we have computed this rotation latency. Now let us see the data transfer time. It is given that data rate equal to 40 into 2 power 10 bytes per second. So in 1 second, we will transfer 40 into 2 power 10 bytes. So time taken to transfer 512 bytes. So our size is 512 bytes. So transfer time will be size by rate. Or we can, this is the formula, or you can figure out like 40 into 2 power 10 bytes will be transferred in 1 second. So 1 byte will take 1 by 40 into 2 power 10 second, plus 512 bytes will take 512 by 40 into 2 power 10 bytes. Okay. Anyway, it comes to the same value. So it is size of so data rate. So which is 512 by 40 into 1024, which is 0.0125 second, which is equal to 12.5 millisecond. Now, final average access time will be, therefore, the average, we can substitute all these values, will be 5 millisecond of seek time plus 5 millisecond of seek time is given as 5 millisecond. Then we found that rotation latency is 5 millisecond, overhead is 1 millisecond, and this is 12.5. Data transfer time of 12.5 millisecond and zero point 0.1 millisecond overhead time, which is 22.6 milliseconds. So this is how when a problem is given, we find the access time. Okay. So now we'll go to the scheduling, discuss the scheduling things and yeah. Yeah, so like CPU scheduling, we have also something called disk scheduling, because there will be a lot of processes which would be requesting data from the disk. Okay. Now, if there is no queuing or buffering available with the disk controller, then all this has to happen serially. Uh, yeah. So let's get into disk scheduling. So if there are no queues or buffer, no queues or buffer with the disk controller, then it will be all sequential. No queue or buffer means it will be sequential. Every the processes will have to wait and it has to wait until the disk read is completed, and then the next request will be taken, and it will happen in a sequential manner. But whereas if there is something called buffering possible, queue possible, then actually the disk scheduler can look at the request which have arrived. If there is a buffer or a queue, it can look at the request disk read requests that have arrived, and then see the best possible way of reading it, such that the seek time can be reduced. Okay, the seek time actually is a time that the head takes to move from one cylinder or one track to another. So if we can reduce this, like if we can plan to read the disks that are located nearby, this reduces the disk the seek time, right? So based on the available requests in the queue, the scheduler can plan the read such that the seek time will be minimized or reduced. Okay, so there are like in CPU scheduling, we have multiple different disk scheduling algorithms, such as we have what is known as first in, first out. Then, like shortest job first, we have SSTF, shortest seek time first algorithm. Then we have seek, we have circular seek, then we have look and circular look. So these are the 1, 2, 3, 4, 5, 6 algorithms that are available for disk scheduling. This is equivalent to the regular FO. FIFO is first in, first out. This is shortest. So in first in, first out, in whichever order the request come, the same order, it will be serviced. Okay. So let's look at the scheduling algorithms with some simple examples. Okay. Mm. So let's take one example request. Yes, the order number cylinder numbers 98, 183, 41, 122, 40, 124, 65, and 67. Okay, so in first in, first out, and it is given that currently disk arm is at cylinder 53. Okay, so in first in, first out, the order in which the request comes, the same order we have to service. So from 53, the currently it is at track number or cylinder number 53. So from 53, it has to go and service 98. So from location from 53 track, it will move to 98. Then from 98, we need to service 183. So number of tracks that the disk arm has to move here will be, it will be 98 minus 53. Here it will be 183 minus 98. Then from 183 to 41, it will be 183 minus 41. Now from 41, it will go to 122. So number of movements needed is 122 minus 41. So it has to move back and forth. So here it was moving in towards the front from 53, assuming that okay, let's assume the inner ones are numbered smaller and outer ones are numbered higher. So 0, 1, 2, 3, 4, 5, etc. Okay, so now, so from 53, the head has to come backwards and read 98. Then from 98, the head has to further come backward and then read 183. Now from 183, we are going forward to 41. Then from 41, again we are coming backward to read 122. So from 122, we'll again go front, go inside. It will again go inside from 122 to read 124. Then from 124, it goes to, sorry, 122, it goes to 14. So from 122, it is going to 14. So it will be 122. The number of movements, number of tracks it has to move is 122 minus 14. And from 14, it's going 124, then 65, followed by 67. So 20 minus 14. This is 124 minus 65, and this is 67 minus 65. So if you see it as a horizontal line, for example, we have the disk arm like this, okay, and it moves this way and this way, this way and this way. For traversing the tracks, we can put this in a line, and if we tell from 0 to 180, maybe 200. So from 53, we can mark all of them here. 14, 41. After that, it is 53. Then we have 65. Then we have 67. After that, we have 98. We have 122, 124, and 183. So from 53, first it goes to 98 here. Then from 98, it goes to 183. From 183, it comes to 41. 41, it go back to 122 here. Then from 122, it's coming back to 14. Then from 14, it's again going back to 124. And then 124, it's coming to 65. From 65, it's going to 67. And from 67, done. We are done, okay, with all the 6. So this is how the disk arm moves in a first in, first out. The order in which it was requested, in the same order it will be serviced. So the number of movements or head movements that had to be done was so number of head movements is 93, 98 minus 53, which is 45, plus 85, plus 142, plus 81, plus 108, plus 110, plus 59, plus 2, which is 632. Okay. So the lesser the number of head movements, better would be the scheduling algorithm, or better would be the scheduling, because as the number of movements reduces, the amount of time we are spending on moving the head up and down is coming down, so which implies better, faster disk access and rate. Okay, so this is how first in, first out algorithm works. So so that is first in, first out. And this in the other algorithm is shortest seek time first. SSTF. So it's same like our shortest job first. So here what happens is it will service the request which is closest to the head. Okay. Service the request tries to at any given point of time it tries to reduce the number of moments to a minimum. So let's take the same example and see in SSTF how it will be. So the it's still 98, 183, 41. The requests are 122, 14, 124, 65, and 67. So with SSTF, it's always easy to sort it and write, or that's 14, 41. And head location is at 53. So currently the head location is at 53. So let's take the number 53 will come here, right? So we have 41 on its left and we have 65 on its right. So which one is closer, 41 or 65? So 65 is closer. So we go to from 53, we go to 65. So that is found out by like simple 65 minus 53 and 65, sorry, do 53 minus 41. So 65, both are same, and it was also given that the head is moving towards the higher numbered cylinder. Okay. We are taking in the forward direction. So we will move from 53 to 65 first. So now 53 to 65 is done. 65 is serviced. Now from 65, 67 is the nearest one. So then 65 to 67 is serviced. From 67, we have 41 towards this end and we have 98 to the other end. So 41 is closer from 67. So we go to 41. Then, so 65 is done, 67 is done, 41 is done. Now, from 41, we have to find the distance between 41 and 14 and 41 and 98. So 14 is closer. So we go to 14. Then from 14, obviously 98 is closer than 122. So we schedule, we go to 98, then 122, 124, and 183. So this is how the order. So the number of, so if we draw it like this, we will have 0 and 200, 0 and 199. So we have 14 here, 41, 53, 65, 67, 98, 122, 124, and 183. So from 53, we go to 65, then we go to 67, then we come to 40, go to 40, sorry, 41, we go to 40, and then we go to 98, 122, 124, and 183. So the total number of movements that is done is 12, 2, 98, 67 to 41 is 26, Then from 41 to 40, 27. Then from 14 to 98, it is 84. Then from 98 to 122, 24, 2, and 59. So the total movement is head movement in case of SSTF is 12 plus 2 plus 26 plus 27 plus 84 plus 24 plus 2 plus 59, which is 236. So if you see here, for first come first serve, we had 632 movements, whereas here we have 236, which is much better. This is SSTF. Let's take one more example of shortest sick time first. So the requests are 434, 10, 7, 19, 73, 2, 15, 6, and 20. Let's draw this. 0, 100. And head is at 50. So we have 2, we have 4, then 6, 7, 8, 9, 10, 15, 19, 20, 34, and 73. 1, 2, 3, 4, 5, 6. Let me write it again. Something the app got closed and the contents are not available somehow. Okay, so the requests are SSTF, SSTF request is in the order 434, 2, 15, 6, and 20. So let's draw the line 0 to 100. We have 2, 4, 6, 7, 10, 15, 19, 20, 34, and 73. So the disk set is head is at 50. So I have 50. So from 50, if I have to go to 34, it will take me 16 moments. Whereas if I have to go to 73, it will take me 23 moments. So to here I have 16, and to here I have 23. So the shortest one is 16. So from 50, it moves to 34. Then from 34, if I have to go, it is to 20 or to 73. So obviously 20 is closer. The number movement to 20 is closer. Then from 20 to 90, this is short rather than going to 73. Then 19 to 15 is short. 15 to 10 is short. Then 7, then 6, 4, 2. Now what is left is 73. Then it goes to 73. So here the number of movements are 16. Then 34 to 12, 20 is 14. 19 to 20 is 1. 19 to 15 is 4. Here 10 to 15 to 10 is 5. 10 to 7 is 3. 7 to 6, 1, 2, and 2. And from 2 to 73, we have 71. So here the total head movements equal to 16 plus 14 plus 1 plus 4 plus 5 plus 3 plus 1 plus 2 plus 2 plus 71, which is equal to 119. So this is about shortest seek time first. Okay, the another algorithm that we have discussed is seek algorithm. So here, this is also called as elevator algorithm. So here what happens is from 0, if suppose we have 200 cylinders numbered from 1 to 199, 0 to 199. So the disk will move from start to 0 to 199. And then during that movement, it will serve all the request which is there on the way. So from 0 to 199, it will move. On the way, whatever requests are available, it will keep serving. Then from 199, it will move back to 0. Here again, while returning back, if it finds any request, it will be served in the order. Then again, it will go to 199. On the way, the request will be served and it will come back to 0. So this is a seek algorithm works. It's like a elevator, like it goes from 0 to 10th floor, comes down to 0th floor, again goes to 10th floor and comes down. On the way, whichever passenger press the lift, they'll get in and then they'll get out. So this is the logic of seek scheduling algorithm. Let's again look at with the with an example. So requests in 98, 183. Again head at 53. Okay. So let's have the 0 to 199. So we have 14, 31, 53 is where currently the head is. Then we have 65, 67, 98, and 183. So it will start from 53, will go all the way to 199. So on the way, we have 65 that will be served, 67 will be served, 98 will be served, and 183 will be served. Now this will come back to 0. So here we have on the way, it will 41 will be served and 14 will be served. Okay, so the time it takes, so the number of movements that this algorithm requires is 50 to 12 to 67 minus 65 to 98 minus 67 is 31. 183 minus 98 is Oh, I missed 122 and 124 in the diagram. Sorry. Keep it here. Um, so we have 122, 124, and 183. Okay, so this is and this one. So here 98 and 122, we have 24. This is 2, 59. Then 183 to 199. Though we don't have any request after 183, the algorithm will go till the end. So this also will come get included in the number of head moves. Okay, 183 to 199 is 16. 16. Then from here it moves to 41. So here it is 158 and then from 41 to 40, which is 27. So the total head movements will be 12 plus 2 plus 31 plus 24 plus 2 plus 59 plus 16 plus 158 plus 27, which is 331, which is higher than okay, this was the same question. Oh, sorry, we lost the questions. It was 236 for SSTF. So this test still not better than SSTF. So this is about scan scheduling. Okay. Now there is something called C-scan. I told it a seek, it is scan. That's okay. Algorithm is scan because it all the way go and okay. Now C-scan is nothing but circular scan. So what the difference between normal scan and C-scan is that here it goes from 0 to 199, come back. So in both the direction, it will serve the request. Whereas in circular scan, what it does is from 0 to 1, if it goes from 0 to 199, it will serve the request on the way. And return direction, it will not take any request. No request will be served in the reverse direction. Then again from 0 to 199 when it moves, it will serve the request. Again it comes back to 0. Then in the reverse direction, no request will be, no read will be done. Again it goes doing reads. So, but return, there is no reading done. In the return direction, it will not be doing any reading. So reading will always be from 0 to 199 in that direction only. So let's see what will be the number of disk movement for the same example with C-scan. Not writing the this one again. 199. Okay. So we have 14. We have 41. Then head is at 53. Head is at 53. Then 65, 67, 98, 1, 122, 124, and 183. Okay. Okay, so when we start from 0, so here, sorry, we have the head at 53. So we are starting from this direction to all the way to 199 before there. So we reach here. On the way, we will service read 65, 67, 65, 67, 98, 1 to 2, 124, and 1 to 83. All this will be read. Then in the reverse direction, there won't be any read done. It will come all the way to 0. Then from 0, it will go all the way to from 0, it will go all the way to 49. In this forward direction, again, the page will be read. So here the number of disk movements needed will be again 53 to 65, it is 12 to 31, 24 to and 59, then 16. Then from 199 to 0, which is 199, then 14 and 27. So here the head moments will be 12 plus 2 plus 31 plus 24 plus 2 plus 59 plus 16 plus 199 plus 14 plus 27, which is equal to 386, which is slightly higher than 331. Instead of doing all this difference, we can actually, if we know, right, from 53 we are starting and the head moves all the way till 199. So whatever requests come in the middle will get served, but the disk will go all the way till 199 because it needs to come back because we have some disk at numbered at 14 and 41 to be read. Right. So another easy way for computing the head count for this scan and look algorithms is like this from 53, it will go to 199. So it will be 199 minus 53 plus then 199 minus 0 plus from here uh, it has to read 41. So it will be 41 minus 0. So this will also come to the same number. That is 146 plus 199 plus 41, which is 386. So this is instead of, we don't need to actually compute the difference because it goes from one point to another. But with SSTF, we have to compute it because it can go in any order based on the shortest, which it's not always guaranteed that it will go to the left or the right. Based on the seek time or number of head movement, SSTF will move in either of the direction. So there we'll have to compute the difference and then do the sum up. But for scan and for look, we can do this. So here also, it's going all the way from 53 to 199. Okay. So this will be also, this also can be computed as 199 minus 53 plus, then in the reverse direction it is serving. So from 199 to this left point, that is 199 minus 40. So that will give the value of 31. So actually there is no, it's not needed. We can do it like this. But for understanding, it's good to start by taking the individual differences. Now the next algorithm is next is look. So the difference between scan algorithm and look algorithm is that in scan, it always goes from 0 to, it goes from this end, then come back, then goes, then come back. That is scan. From this end to this end it goes. Whereas in look, it will start, it will go, for example, if this is the like 199 and if the request is 183, it will go only till 183. It will not go this distance, it will not traverse. Then from 183, it will come till here. Then it will go here wherever needed. It will come. It's not like it's always go to 0 to the both the extreme points. It's not like that. So when it will go to the rightmost cylinder or track it wants to read, then it come back and read, and then comes until the leftmost cylinder where the requests are pending. Then again it goes till the rightmost cylinder where the requests are pending. Again till the leftmost, not to the first and last, 0 and 199. So that's one major difference between the but for scan it will always go till this end. So let's see the same example for look also. Yeah, so head is at 53 and our line is 0 to 199. We have 14, 41, 53, 65, 67, 98, 122, 124, 1, 24, 183, and 199. I am writing till 199 because the number of cylinders are, we have 200 tracks or cylinders. 0 to 199. Okay, this is where the head is. So when we have, so with speed, so with look, we will start from 53. We'll go all the way till the leftmost disk, which needs to be read. So we'll all the way go till 183. Then we'll come back till the rightmost. So on the way, we will read 65, 67, 98, 122, 124, 183, then 41 and 40. So here the number of head movements will be from 183 minus 53 plus 183 minus 40 and 30 plus 169, which is 299. So this number is better than the seek, because in seek we were traversing this additional distance also. Additional movement also was coming up. So that is less for look, because we are only going till the rightmost point from where we need to read. We're not going all the way till the top floor or the highest end point. Okay, so this is about look. So we have a circular variant for look also, which is called as C look. That is circular look. So circular look is same like a C scan. So here what we do is it will go in this direction, read whatever is there, come back, there won't be any reading. Then again, only in the forward direction, reading will be done. In the reverse direction, there won't be any reading. Same like circular C, but applied on the look algorithm. So let's take the same example where this is 53, head is at 53. So 14, 41, 53. This is where the head is. 65, 67, 98, 22, 24, and 183. This is 1. So we start from 53. We go till 183. On the way, we read all these cylinders. Then in the reverse, we come till this point, but in the reverse direction, we will not read anything. We'll come back to 40 and then it will go till 41. Then it will read here and then it will read. So here again, yeah, we can see that we are saving this and this, but we did save that here also. We had saved that here also, but in with respect to C scan was actually going till here, and then we will trace this point and this point. So this additional to tracing is saved in CLOOK. Okay. So here again the moments will be head moments. From 50 through 183 minus 53 plus from all the way 183 to 14 plus 41 minus 40. So this is 130 plus 169, 326. This is higher than the previous one, the normal loop, because we are not serving any request in the reverse direction. Okay. Let's take one more example of C loop. And after this, we can go back to the previous year questions. To request our C loop scheduling policy. Head at 63. Requests are 47, 38, 121, 191, 87, 11, 92, and 10. So 10, then we have 11, we have 38, 47, we have 63 is where the current head is. We have 87 after that, then 92, then 121, and 191, and okay. So head is at 63. So we start here. it is C look. So we will go all the way till 191. On the way, we will read 87, 92, and 121. Then we will come all the way till it is C look. So we come all the way till 10, but we will not read any request, any data from any of those tests. Then again we'll go all the way till, then we'll read 11, 38, and 47. Okay, so the head movement will be, total movement is from 63 to 191. So 191 minus 63 plus moved from 91 to 10. 191 minus 10. 10 plus from 10 to 47. Which is 128. 128. Mistake. 63. 128 plus 181 plus 37, which is equal to 346. So we have a total of 346 head movements. So, and just one more question before we go back to our previous year questions. So, yeah, so it's given that we have 200 tracks and requests. If you have any question, you can unmute and speak, or you can put it in the chat and check it. So 200 tracks and requests are, we have 200 tracks and requests are in the order. Requests are in the order 36, 69, 167, 199, 12, 36, 42, 51. Oh, sorry. 36, 69, 167, 76, 42, 51, 126, 12, and 199. Okay. Arm is at 100th track, moving towards 200. Sequence of disk access is 126, 167, 199, 12, 36, 42, 51, 69, and 76. Which scheduling algorithm is used? Okay, so let's draw this and find out. Okay, so from we have 200, so we have from 0 to 199. So what are the points? One is in the increasing order. Let's write down them. 12 we have. 12 and 20 is something. 36. Then we have 42. Then 51. 69. 76, 80, 90, 100, 126. Then, okay, I will just mention the 100 is where the disk head is. 126 we have. Then we have 167 and 199. Okay. So these are the disk access. But the access sequence is given as 126, then 167. Okay. Then it is have access to 199. Then after that, it have come to 112. Then after 12, it have access 36, then 42, then 51, then 69, and 76. So this is an example of, see, from 100, it is going in the forward direction. It is going till 199 and 199 is there in the request also. Okay, then it is coming in the reverse direction all the way to 12. So it is, we have to note that in the reverse direction, if it was a scan algorithm, then it would have um, uh, if it was a non-circular scan or look, okay. If it was a non-circular one, it would have accessed the request in the return direction also. So since in the reverse direction there is no access, it is a circular variant. Okay, it's a circular variant of scan or look. Okay. Now how do we identify whether it is scan or look? You see here, from 199, we cannot identify because 199 is already there in the list. So we can't be sure whether it was a scan or a look. If it was look also, it would have gone till 199. If it was scan, it would go with till 199. So see, in the reverse direction, since there is no axis, we concluded that's a circular variant. But a circular variant, there is scan and look. So now let's see from 199, is it going to 0 or not? If it is going to 0, then it is a scan. But it did not go to 0. It went only till 12, which implies that it is a look. So the scheduling is C look. So this sequence given, given sequence pertains to C-look scheduling algorithm. Okay, now let's go back to the previous year question papers. Yeah, so the first question is disk has 300 cylinders. Disk has 300 cylinders. If the initial position of the read-write head is at cylinder 101, calculate the total head movement following the SSTF. I'll come back to this too because I again need to share the other screen. We'll complete the other MCQs and come to these two questions. So in which of the following algorithm, the disk arm starts at one end of the disk and moves towards the other end, servicing request till the other end of the disk. At the other end, the direction is reversed and servicing continues. So it is done in scan actually. It will start from one end to the other end and then in the reverse direction. So the answer here is scan B. The time taken for the desired sector to rotate to the disk head is called time taken for the desired sector to rotate to the discuss positioning time, random access time, seek time, rotational. It is the rotational latency. So time it takes for the disk to rotate so that the respect correct or the required sector comes under the read write head as the rotational latency. So the answer here is D. The next question, what is the primary reason that a translation look aside buffer is used? Is the primary reason. A TLB ensures that a process does not access memory outside its address space. TLB makes translating virtual address to physical address faster. TLB allows multiple processes to share L1 cache. TLB makes translating virtual address to physical address possible. So the primary reason is to increase the what to say um, the conversion time, like make the virtual to physical memory address conversion faster. So if you don't have TLB to read the particular page, first we need to read the page table and then we need to read. So we were having two memory access to avoid this double memory access. We are putting the page table into TLB. So that basically page table is used to get this conversion. So TLB actually makes the translating virtual address to physical address faster. So the answer here is B. Which of the following is not a way to make file systems faster? Put parts of a file on many different tracks. So part of it can be accessed no matter where the disk head is. Cache frequently use blocks in memory, so they can be accessed at memory speed instead of that is a way to make it faster. Use a disk scheduling algorithm to minimize the distance between seek. That is true. Put frequently used files or directories near the center of the so on average they won't be far from the read and true. So the one way to not make it faster is a put parts of the file on different tracks. So part of it can be, we actually try to put it on same track sometimes so that the parallel access should be possible. So here the answer is option A is wrong. Next question, for a system that performs heavy load on the disk, which of the following disk scheduling algorithm is more suited? Yeah. So someone with heavy load, C-scan is suited because always there will be something or the other to be read from all of the tracks scattered across. So answer here is the scan. Next question. Consider an operating system capable of loading and executing a single sequential user process at a time. The disk head scheduling algorithm used is first come, first serve. If FCFS is replaced by shorter seek time first and the vendor claims 50% better benchmark results, what is expected improvement in the IO performance of the user program? So here the catch is that an operating system capable of loading and executing a single sequential user request at a time. So at any given point of time, it's a sequential and there is only single user process, right? So there is no buffering or queuing, nothing. It's sequential. So the scheduling comes in when there is buffering and queuing. So here the expected improvement in the IO performance of the user program will be 0% only, because it is in the it's a single process sequential, single sequential user process, right? So after the one, if it will have given one request, that will be served and the next will be taken up. So that will not have any impact on the performance of the IO performance of the user program. Which of the following are problems of contiguous allocation? Finding space for a new file, external fragmentation, compaction requirement, and all of the above. Yeah, it's like if we want to go for contiguous allocation, we need to find a large enough space. And for a file, for example, earlier we had a whole of like 100 KB and we used that. But if the size of the file increased to 150 KB, and if that is no longer fitting in that, then we need to find a different place where all this 150 KB can be loaded. So finding space for a new file in case of contiguous allocation is a difficult task. And then external fragmentation, we will be actually taking a larger hold to fit in the memory file. So there is always a possibility that some part of that allocated memory is not being used, and this leads to external fragmentation. So as external fragmentation, small holes will be scattered across, and these holes will be unusable. But if we bring them all together using compaction, we will be able to use it. So it leads to compaction requirement. So the answer here is all of the above. Match the following columns according to the most accurate disk. File access type is sequential or random. Then if the file access type is sequential or random, then uh, contiguous allocation is what is chosen. Access type is declared at the creation, then contiguous or linked allocation is used. And if file access type is sequential but not random, then linked or contiguous allocation is used. So I did not discuss about file access in this class. We'll come back to this there is one more session planned on Tuesday. So in that session, we'll discuss about the files, what is linked storage, contiguous allocation and all that. And then we'll discuss this problem there once again. Okay. Yeah, so we'll just quickly take a look at this problem, and then we'll wind up today's class. So the question is, Yeah, we have 300 cylinders, 0 to 299. And initial head position is 101, and SSTF is the policy, and read request sequence is 123, 45, 197, 87, 250, 198, and 280. Okay, 0 and 299. So 45, we have 45, 87, 101, 87, 123, 197, 198, 280, 199, 250, 250, 289, and 299. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All of them. Oh, this is 280. Okay. So, in 101 is where the current head is. So, we have to see the distance from 101 to 87 and 123. Okay. So, from 101 to 87, it is how much is the distance? 101, 87, 97. Is 14, right? Yeah, it is 14. So 101 to 87 is 14. Whereas 101 to 123, it is 22. So which is larger. So to 87 is closer. 101 to 87 is short. So we traverse from 87 first. Then from 87, we see which one is farther, 45 or 123. So 87 and 107. So it's around 40, whereas this is 40 plus 2. 45, it is 87 minus 45 is 42. Whereas 123 minus 87 is, I think, 36 or so, which is less than 40. So from 87, we go to 123. Give me a minute. Yeah, so from 87, it goes to 123. This battery got drained. So from 87, it goes to 123. Yeah. So from 87, it goes to 123. Then from 123, it can either go to 197 or 45. So this is a shorter distance. So we traverse 197. Then 197 to 198, it is only a shorter distance. Then 198 to 250, then 250 to 280, and then from all the way back to 280 to 45. So this is the shortest seek time first traversal. So the distance or distance traversed is this is 14, and from 87 to 123 is 36. Then 123 to 97 is 74. Then it is 1, and then 52, 30, 52, 30, and then 280 to 45 is 235. So the total number of head traversed is 14 plus 36 plus 74 plus 1 plus 52 plus 30 plus 235, which is 442. So this was one question, and the other question in the previous year question paper is on C-look policy. Again, the same. This one, 123, 45, 197, 87, same thing, but C-look. And cylinder is at head at 101. So let's do that also, running of time. 0, 45, 87, 101, 123, 197, 198, 250, 280, 29. It is C look. So we'll start from 100. We'll go all the way till 280. C look. So it will go all the way till 280. Then it is cyclic. So it will come back to 45. But in this direction, there will not be any reading, and then it will go to 87. So here the number of axes would be 280 minus 101 plus 280 minus 45 plus 87 minus 45, which is equal to 80 minus 101 is 179 plus 20 minus 45 to 35, 27 minus 35, 32. Which is 456. Okay, yeah. You can actually compute the difference, but this is easier since it's moves, like it's easier to compute the head move. So 456 is the answer here. Okay. So with this, I'll wind the session for today. We'll again, I'll have a session on coming Tuesday from 6 to 8. That time we'll discuss the file system and its allocation, like linked allocation, contiguous allocation, indexed allocation, hierarchical indexed allocation, etc. Yes, thank you. Thank you for joining. Thank you.